Okay, after this quick break, let's get back to it. Our goal was to find tractable graph classes that go beyond the measure of sparsity that we talked about so far in this course. And so far, the most general classes of graphs that we discovered where you can do first order model checking would be nowhere dense graph classes. And for monotone graph classes, this is actually the limit of what is currently possible. But we already briefly talked about some other dense graph classes, which are those with bounded clique width. So earlier in the lectures, we discovered that clique width can be considered as a dense analog to tree width, and that you can still do first order model checking on classes with bounded, or you can actually do MSO model checking on classes with bounded clique width. So I won't repeat the definition of clique width again. It was this kind of construction sequences using relabelings and disjoint unions of colorful graphs. But the important 2 bits are the following: that clique width generalizes tree width. So if a graph has tree width at most W, then the clique width is at most 3 times 2 to the W minus 1. So this implies in particular that every class with bounded tree width also has bounded clique width. And additionally, you can evaluate MSO1 sentences on graphs with bounded clique width in FPT time. So the running time that you get is some function of the clique width of the graph and the formula length time n to the 3. So on graph classes with bounded clique width, you can do MSO1 model checking, which means you can in particular also do first order model checking. So this is now our first example of a non-trivial dense graph class where you can do first order model checking. So everything here is sparse, but this is kind of the dense world already. And we would like to explore some more aspects of the dense world where you can still do first order model checking in FPT time. And we're going to start with a very trivial example, which would be complements of nowhere dense graph classes. So a graph class is a complement of a nowhere dense graph class is if you can complement each graph in the class and you get a nowhere dense graph class. And it's quite simple to see that complements of nowhere dense graph classes are also tractable. So here's a simple example. So let's assume we want to evaluate some formula phi on a graph G, and G or G bar, and G bar is complement of some sparse graph G. So then this means 2 vertices are adjacent in G bar if and only if they're non-adjacent in G. That's the definition of a complement. So in other words, here, whenever 2 vertices are adjacent, this is the same as saying they're non-adjacent in the complement. And this is what we can use in our reduction. So this formula phi, it contains atoms that state some vertices should be adjacent or some vertices should be non-adjacent. And we can create a formula phi bar, which just swaps adjacency with non-adjacency and the other way around. And this formula phi bar then holds in the original graph if and only if the original formula holds in the complement. So this is because taking the complement of the graph and taking the complement of the formula, these 2 operations cancel each other out, and 2 vertices are adjacent in the complement if and only if they are non-adjacent in the original graph. And here, if this is coming from a sparse graph class, you can do FPT model checking, and the formula phi bar it's the length of it still constant. So this then gives you the answer for the dense class. So very simple argument that shows that you can do FPT model checking on complements of nowhere dense graph classes. But this was too simple. I think we need to consider some more complicated classes derived from nowhere dense graph classes. And how about the following? So what about FPT model checking on the class of fully bipartite graphs? So this fully bipartite graph, it is not nowhere dense because that's what we discussed in the last exercise. Large fully bipartite graphs contain large cliques as depth 2 minors. So this is not nowhere dense. And also if you take the complement of this graph, and all these edges are removed, but these two halves get turned into cliques. So also the complement of this fully bipartite graph is not nowhere dense. So we cannot do the trick that we discussed earlier, where you just take the complement of the graph and evaluate a modified formula there, but we can do something quite similar. So let's consider this graph here. It has the same vertices as G, but it also has these two orange vertices. And we notice that two vertices, X and Y, are adjacent in G if and only if they have distance 3 in G prime. So distance 1, 2, 3. So everything, if X and Y are on different sides, they have distance 3. On the other hand, if X and Y are on the same side, they have distance 2. So what we notice is that X and Y are adjacent here if and only if distance X and Y is equal to 3 in this graph G prime. So G prime is a tree, and we could do first order model checking there. Trees are tractable for us. And now I want to do a similar kind of reduction that we talked already here. So instead of asking our formula phi whenever it asks whether two vertices are adjacent in G, instead we can evaluate the formula in G prime. And whenever we ask whether two vertices are adjacent, we replace it with an atom that checks whether the two vertices have distance exactly 3. And this creates an equivalent instance. So we can obtain phi prime from phi by replacing each atom X adjacent to Y with a different atom X and Y have distance 3. The only extra thing is that there's these two extra vertices that we need to get rid of. So we also need to restrict the quantifiers of phi prime to only using the black vertices. But then we have an equivalence instance. And where do complete bipartite graphs fit into the picture? They would be kind of, I don't know where they would be, but this is not interesting, but it's more as a motivation of a more general principle that we call transductions. So we're going to consider next transductions of nowhere dense graph classes, which contain both the complements and the original graphs, and it's a very nice concept. So before we define transductions, let's first consider interpretations. So an interpretation is a function that maps a graph G to the graph I of G. And interpretation, it depends on two formulas, contains the formula mu of xy with two free variables and the formula mu of x with one variable. And if the input graph is G, the output graph I of G will be drawn here on the right. And how is it constructed? First, the vertices of I of G are all the vertices that satisfy mu in the original graph. So for example, if mu is the formula x is black, then all the black vertices would be contained in I of G. In particular, those two orange vertices would be dropped. So all the vertices satisfying mu will be included in the graph, and which edges will be included? As you have guessed already, all the edges satisfying mu will be, or all tuples satisfying mu will be included in the output graph of interpretation. So if two vertices have distance 3 like this, then there would be the edge between them would be included in the output of the interpretation. So that's an interpretation. It maps one graph to another graph. And we're going to use it to do model checking. So assume you want to know whether phi holds on the output of some interpretation, like on this graph. Then you know that there's an edge between two vertices if and only if they have, if and only if they satisfy mu of x, y. So instead of asking whether x and y are adjacent in the interpretation, we can instead ask whether they satisfy mu in the original graph G. So we can build a new formula phi that checks, instead of an edge relation, checks whether two vertices satisfy mu, where mu is the formula that is contained in the interpretation. And then instead of evaluating formula on the interpretation, we can evaluate mu on the pre-image of the interpretation on the graph G. Okay, this is why interpretations are an interesting concept. If you know that a graph is an interpretation of some other sparse graph and you can actually compute the interpretation, then you can do model checking. But interpretations are not quite enough. We need a little bit more of a complicated concept called a transduction. So we say that a class C is a transduction of a different class D. Just talking about graph classes here. If there exists an interpretation such that every graph G in C, there exists a pre-image H of D and the coloring H prime of this graph such that G is the interpretation of H prime. So in other words, it means C is a transduction of D if every graph in C can be derived from some graph in D by first doing a coloring and then doing an interpretation. The important bit is here that the interpretation needs to be the same for every graph. You have to fix the interpretation beforehand in order to construct every graph in C. So in order to digest this definition a little bit more carefully, let's take an example of a transduction. So I want to show that if you can set C to be the class of bipartite graphs and D to be the class of trees, then C is a transduction of D. So in other words, the class of complete bipartite graphs is a transduction of the class of trees. How do we show this? We just follow along the definition. The definition says there exists an interpretation I, and in our case, interpretation I will be the one that selects the black vertices and as edges chooses the vertices with distance 3. And the next line says such that for every graph in C, so let's take an arbitrary complete bipartite subgraph G, there exists a graph in H, there exists a graph H in D. So here's our graph H. And the coloring H prime of H, the coloring is just gonna color these two vertices as orange, such that G is an interpretation of H prime. And that G is an interpretation of H prime is something that we discussed already. Okay. So here we have an example of how a transduction can map one graph class to another graph class. And with this notion, we have formally defined transductions of nowhere dense graph classes. So a transduction of a nowhere dense graph class is basically everything that can be derived from a nowhere dense graph class by coloring the graphs and then applying a fixed formula interpretation. And the big question is now whether model checking is FPT on transductions of nowhere dense graph classes. So we believe that this is the case, but we don't have any proof of this yet. So a good way to start would be, because it is a transduction of a nowhere dense graph class, then this is the same as evaluating the interpretation of G, and where G is the coloring from a nowhere dense graph class. And if we could compute this graph G, then everything would be fine. We would just do this trick that we discussed earlier by modifying the formula a little bit and instead evaluating it on the pre-image G. But apparently this is quite hard to do. We don't know how to compute this kind of pre-images. But there have been some partial results on this yet. So for some sparse graph classes, we have a model checking algorithm for the transduction of them. So the first one of this kind was transductions of classes with bounded degree. So first order model checking is FPT on transductions of classes with bounded degree. And the second result of this kind, very fresh, straight from the oven, be careful when you eat it, still warm, is the following. It states that if C is a transduction of a class with locally bounded tree width, then model checking is still FPT on this class. So locally bounded tree width includes bounded degree, but does not quite bring us all the way to nowhere dense graph classes. So this is some good evidence, I suppose, that transductions of nowhere dense graph classes might be tractable, because so far we've come all the way to transductions of locally bounded tree width. Maybe later on we can push it on to transductions of nowhere dense classes. But this is still not the complete picture. So this notion of clique width kind of sticks out. It is not contained in the transduction of nowhere dense graph classes. This is because clique width can contain very large orders or half graphs, and this is something that transductions of nowhere dense graph classes don't contain. And the picture gets even worse because there is a notion of twin width, which generalizes clique width, but is not comparable to transductions of nowhere dense graph classes. So let's maybe talk about what twin width is. So you know how normal graphs work. You have just edges and non-edges. But twin width uses the notion of trigraphs. So in a trigraph, there's normal edges, which are drawn black. There's non-edges, and there's additional red error edges. And here we have these 5 red error edges. And twin width uses these error edges in contraction sequences to keep track of the errors that will happen. And yeah, we have these trigraphs, and in twin width, we need so-called contractions between 2 vertices. So if we have a vertex A and a vertex B, they don't need to be adjacent, but they can be, then we can contract them into a new vertex AB, and the new vertex AB, it will be adjacent in a certain way to the neighbors of A and B, and the way the adjacency is worked out is defined here in the upper table. So if A is non-adjacent to a vertex and B is also non-adjacent to a vertex, then the contraction of A and B will also be non-adjacent to a vertex. For example, this guy here, it is not adjacent to A, it is not adjacent to B, so they both agree here. So in the contraction of AB, it would also be not adjacent, the contraction to this vertex. The same holds if A and B are both adjacent to a vertex, like this one, then the contraction A and B will also be adjacent to this vertex. On the other hand, if A and B do not agree, like, what is it, this vertex, for example, B is adjacent to it and A is non-adjacent to it. In this case, we create a red error edge between A and B. Now a red edge is introduced here. The same holds if A is adjacent and B has an error edge to a vertex, or as soon as there's one error edge to a vertex, there will be an error edge also in the contraction. Okay, so this defines contraction of 2 vertices. If 2 vertices agree on a neighbor, you create a non-edge or an edge, and as soon as there's an error edge or the 2 vertices don't agree on the neighborhood, you draw a red edge to a neighbor. So this was what happens to how you create the neighborhood of a contracted vertex. All the other vertices stay the same. And here's an example of how such a construction sequence may work. So we start with this graph, and the contraction sequence simply starts with the graph and then contracts and contracts and contracts until only a single vertex is left. So let's see such an example of a contraction sequence. For example, we could start with contracting E and F. The vertex C is adjacent to both E and F, so in the contraction, it is also adjacent to the contracted vertex. On the other hand, A is only adjacent to F, but not adjacent to E. So the two vertices don't agree on the adjacency to A, which means in the contracted vertex, there will be an error edge to A. Okay, so this was the first contraction, contracted E and F into a new vertex. And a contraction sequence does this until no vertex is left anymore. So when we contract A and D, update the red error edges to the neighbors accordingly, and we repeat it, merging, contracting, until only a single vertex is left. And this is what we call a contraction sequence. And now finally, I can give you the definition of twin width. The twin width of a graph is the smallest integer d such that there is a contraction sequence where the red degree of the graph is at most d at all times. So every vertex should have at most d red outgoing edges. So let's use this to figure out a bound on the twin width of this graph. In the beginning, there are no red edges, but now after the contraction, the vertex EF has red degree 2. So the maximal red degree so far that we've seen in the contraction sequence is at most 2. Continue. Now A and D are contracted. It has also degree at most 2 red degree. And we continue. Still red degree at most 2. And so forth. So this contraction sequence is therefore a witness that the twin width is at most 2 of this graph, because at all times the red degree was at most 2. And twin width, there's some examples of classes that do have bounded twin width. For example, again, we say a class has bounded twin width if there exists a constant d that bounds the twin width of every graph in the class. And for example, trees have bounded twin width, grids have bounded twin width, also classes with bounded clique width. So twin width is a strict generalization of clique width. So it's quite powerful. On the other hand, planar graphs or graphs with degree at most 3, they don't have bounded twin width. So twin width is a little bit strange. These graphs that sound quite simple, like graphs with bounded degree, they do not have bounded twin width. So it does not necessarily capture everything that appears simple, but it generalizes still many dense graph classes that are tractable. And the big open question with respect to twin width is to compute these contraction sequences. So far, we don't know how to compute them or how to even approximate them. But if we do, then model checking becomes FPT, because there's this very nice conditional result, which states that first order model checking is FPT on classes of bounded twin width if we assume that the model checking algorithm additionally gets some witness of the contraction sequence. You additionally get a proof that the contraction sequence has that the twin width is at most d. And I have to retract some information that I wrote on the last slide. Planar graphs do have bounded twin width. Sorry about that, and thanks. Okay, Great. So if we could construct these contraction sequences, then model checking would be FPT on classes with bounded twin width. That's why I've drawn this a different color, because so far we don't know whether you can do model checking there, but we have a good idea that, or we at least have a reason to hope that it should be possible. And this is almost the complete picture. So we're of course hoping for a big unifying theorem that our measure of graph classes that captures both twin width and transductions of no dense graph classes. So something that looks like this, a big width measure that contains everything where first order model checking is tractable. And it has been conjectured that this is something that we call monadically nip. And let me give you a definition of this again. So we need the notion of transductions. So a graph class C is a transduction of D if every graph in C can be derived from a graph in D by coloring the graph and then applying interpretation. And then the graph class would be monadically nip if a graph class C is monadically nip if every transduction D of C is not the class of all graphs. So you want, you try to forbid that the transductions of a graph class are very complicated. And if you cannot transduce all graphs from a graph class, then we say it is monadically nip. And it is conjectured that monadically nip captures exactly those graph classes where first order model checking is tractable in FPT time. So this should have just been like a very rough overview of what the state of the art is right now with respect to model checking on dense graphs. It's still an open field, an active area of research, and I invite you to contact me if you're interested in this for master's theses or research or anything. And I think now we've reached the end of the lecture. Thanks for coming along on the journey. It was quite fun to teach this, and I hope you enjoyed it too and got something out of this. Thank you very much, and have a nice day. And see you for the exam for those of you who want to take it.